The title of the presentation is Effect of Geometric Parameters on the Heat Transfer Performance of Computer CPU Coolers. I am Shubho Das, completed my MSc Mechanical Engineering from the Southern Illinois University at Edwardsville. Dr. Majid Mulki, Distinguished Research Professor at the same university, supervised me in this study. At the beginning of my presentation, I would like to highlight the topics that I am going to discuss next. Mm, Here we talk about what is a CPU cooler, what are the purposes of the study, how I mathematically modeled it, the discretization error, and then I compare my work with the literature, and I draw a Nusselt number correlation for the existing CPU cooler. Then I talk about optimal arrangement of CPU components, and finally I talk about application of this research and concluding remarks. The CPU cooler investigated in this study is an air-cooled desktop CPU cooler, which are comprised of fan, base plate, heat pipes, and many plate fins. The heat transfer mechanism is simple. That base plate sits at the top of a processor and collects the heat from the CPU. This heat is then transferred to the plate fins by means of heat pipes. And when this fan blows air through the air gaps in between the plate fins, the heat is transferred to the surrounding air. Our investigation started modeling a CAD design out of these, where our goal remains understanding the design parameters that cause overcooling and undercooling of a CPU, obtaining the Nusselt number correlation, and understanding the key geometric parameters. From the whole CPU cooler, when we selected the computational domain, we looked at the one fourth of the whole CPU cooler, and we took one half of a single plate fin and one half of a single air gap in this direction. And we see that in the selected computational domain, we have heat pipe 1, heat pipe 2, air in and out directions. There are three air out directions and two symmetry planes as well. And if we zoom into this corner portion, we see the plate and air segment separately along with the coordinate systems. For the air segment, we have continuity, momentum, energy equations as shown here, and for the plate, we have heat conduction equations also listed here. And our assumptions are steady state incompressible Newtonian fluid with constant properties. We put boundary conditions like prescribed temperature and velocity at the air inlet, at the outlet, zero gradient, and for the symmetry patches, we put sleep boundary conditions and no sleep at the air and fin interface. Also, at the interface, temperature and heat flux are equal. Then we performed grid study from coarse mesh to fine mesh, having a cell count of 52,000 to almost half a million, and we computed the Nusselt number. And for this range of grid size and number of cell, we found that Nusselt numbers change is very minimum. The detail of this grid sizing is shown here as we modeled our blocks. Modeled our computational domain using block mesh of OpenFOAM, where we had three blocks: block 0, block 1, block 2, and we had to discretize all of those blocks separately. But for simplicity, we didn't show all those details in this table. But these cell counts comes from this detailed discretization of this domain. Once we have a grid independent computational domain, we want to investigate changing the Reynolds number from 100 to 2000, changing the heat pipe temperature from 35 to 95 degrees Celsius, and keeping the inlet air temperature 300 Kelvin, which is a regular scenario in case of a conventional CPU cooler, desktop air cooled CPU cooler. And then we calculate the heat rate and Nusselt number using these equations. And If we look at this table, there are five Reynolds number: 100, 500, 1000, 1500, and 2000. And for each category of Reynolds number, we changed the heat pipe temperature from 35 to 95 degrees Celsius. And in the output, that is Nusselt number, we see that Nusselt number is changing with the change in Reynolds number only. But if we look at the same Reynolds number, when we change the heat pipe temperature, Nusselt number remains same. So that tells us Nusselt number is a function of Reynolds number and not a function of heat pipe temperature. But we have a fixed Prandtl number in case of our working fluid, that is air, in this study. Using this table, we can easily plot Nusselt number versus Reynolds number as shown here. Also, at the same time, we compared our plot with another referenced finding that is shown here. We see a slight difference due to the change in flow field, geometric dimension, and also the number of heat pipes considered, but they are in a similar trend. Also, from this plot, we drew two correlations in terms of two heat pipes, Nusselt number 1 and 2, and we compared this correlation with another experimental work, that is when circular cylinders are placed in cross flow, the Nusselt number correlation exponentum should lies in the range of zero point 0.4 to zero point 0.6, which is matching with our correlation. Now we want to change the range of geometric parameters. Some important geometric parameters are fin thickness, air gap thickness, heat pipe diameter, fin length, and fin width. We can talk about in terms of CPU coolers. So if we look at this, we have changed all those parameters: fin thickness, air gap, heat pipe diameter, fin length, and width. And in a manner we changed that we decreased first the original parameter, and then we increased one step forward the original parameter. For example, if we look at original heat pipe 2 diameter was 8 millimeter diameter, then we lowered it to 4 millimeter diameter first, and also we increased that heat pipe 2 diameter to 16 millimeter diameter as well. So when we changed one parameter, we kept the other parameters same, and our uh, discretizing the mesh and the ratio, I mean aspect ratio, and computational domain meshing, and all those parameters, we tried to keep them in a similar fashion, so that we can generate same we can generate good results out of those computational results. So from those findings, we tabulated Nusselt number, heat rate, pumping power, and heat rate and pumping power ratio as tabulated here. And from this table, we plotted some plots based on Reynolds number of 500 and Reynolds number of 1500, and computed parameters like pumping power, Nusselt number ratio, heat rate, and heat rate over pumping power as shown here. So out of all those parameters, two crucial parameters came out to be air cap thickness and heat pipe diameter. And we see that when we decrease air gap thickness from 2 millimeter to 1 millimeter, we see increase in the heat rate and increase in the pumping power as well. And the other one, that is heat pipe diameter, we see that when we increase heat pipe diameter from the original 6 millimeter to a diameter of 12 millimeter, there is increase in pumping power and increase in heat transfer as well. The other parameters doesn't affect that much compared to these two parameters, air gap thickness and heat pipe diameter. If we look at the velocity contours, when they are drawn in terms of Reynolds number of 500 and 1500, relating to the previous slide, we can see that when we decrease air gap, U magnitude increases drastically, and when we increase heat pipe diameter, this magnitude increase drastically, and that causes the heat transfer to rise and at the same time pumping power to rise. Because when we increase it is physically sensible as well. When we increase the heat pipe diameter, we need to employ more pumping power, and there are local increase in velocity due to this heat pipe bigger shape. Another one is temperature contour we want to look into, and we see that this bigger heating zone, I mean hot zone, for this decreased air gap scenario, the heat transfer rate increases. And for the heat pipe to diameter increase, we see higher heating zone, I mean hot zone increase in hot zone behind this heat pipe, and this also increases the heat transfer for this type of setup of computational domain. And there are similar trends found in terms of Reynolds number of 1500 as well. This study can be served as a model to obtain conjugate Nusselt number correlations. Also, it points out the key parameters that dictate optimized CPU cooler design. As concluding remarks, the major findings of this research are increase in heat transfer rate is small with the increase in fin thickness. Number two, increase in the air gap increases the heat rate to pumping power ratio. And then increase in heat pipe diameter is advantageous to heat transfer because, I mean, increase in heat pipe diameter is advantageous to heat transfer, but it costs more pumping power. Nusselt number ratio, heat rate, pumping power, and the ratio of heat rate to pumping power all remain approximately the same, corresponding to the change in fin length and width as investigated in this study. Thank you.